All right. Thank you. Thank you very much for the kind introduction. And thanks for inviting me here. It's always a pleasure to be in Munich. I've been here now many times. And now it's even more fun to be here because I can see that you keep adding a lot of good old friends from back in the day. So there are more and more reasons to come here. All right. So what I'm going to talk about is making photons interact. And yeah, we have a lot of work on this during the past years together with my colleague Peter Lodal, where we are sort of ping-ponging back and forth. Right. So the idea is that we want to make photons interact, and there are many good reasons for that. Nonlinear optics, quantum information science, Bell state measurement. There are a lot of things you can do in quantum information science if you can make photons interact. Right? We like to use photons to transmit information over long distances, and therefore we would like to also be able to manipulate that information encoded in those photons. Now, this is what I spent most of my time working on. How do we make, quantum information protocol? But actually, this project here more came out of me some 5 years ago, wanted to take a break from that. So I just wanted to do some fun physics. So this year is now playing around with photon interactions just for the fun of it. So now I will just think about this as an interesting physical system. It can probably be used to some of this stuff up here. This one is hard to control for quantum information science. And, some of the work that came out of this, we took a patent on even, but yeah, mainly I just wanted to do some fun. All right. So why are photon interactions fun? Well, I think this was probably my first encounter of photon interaction. Right, you have these people battling with lightsabers here. And what is very clear is that there is some very strong photon interactions going on here. Right, normally light beams just pass through each other, but in this system, there apparently seems to be a very strong photon interaction. Right, so what I want to do today is look into the physics of Star Wars. Although I should admit that I have absolutely no explanations for what happens up here. But let's just look at this one here. Now, of course, with a group of physicists, one should be careful about making Star Wars jokes because sometimes our community can be divided on this issue. So to the rest of the people, I would just say, don't worry, there's a Star Trek reference coming up later. All right. So, but now you can ask, why is this thing here so fascinating? Why do I think that it is cool that these photons interact? Well, I mean, the issue is that why we think that this is so cool when it happens is that normally photons don't interact, right? So suddenly you see these people here fighting with lightsabers and their photons collide. It's fun, it's different physics. So this is basically why I thought it would be fun to see what can we do with photons interacting. All right. So, but now back to more serious physics, of course, involving Feynman diagram. So sort of the Feynman diagram you'll be playing around with is this one here. So you have two photons coming in, and this one here creates a particle hole pair that collides with a different photons, and out come two other photons here, right? So this is the basic Feynman diagram, and we want to see this diagram where the input photons are individual photons, one coming in here and one coming in here. Now, this diagram here, of course, if you try to do it in vacuum, it is completely negligible. People have tried to see it with strong laser beams. I don't think they have succeeded simply because you need very strong lasers at very high frequencies, and people haven't been able to see it. But of course, what we can do and what we do in this quantum community is we design systems where we can sort of enhance the processes that we like, okay? So we can design media where this process is actually strong. And there are a number of different approaches. One of them is very popular here, and that is we would like to do it with a single atom. So we have this single atom here, and what we do is that we put some mirrors around it, and then we have an optical cavity, and we can have strong interaction. And in particular, what we can do is we can send in a photon. This photon here bounces around a few times, and in the end, it gets absorbed in the atom. Now we can take another photon, we can send it in, and what will happen is because of this photon here that is absorbed in the atom blocks the cavity, then the second photon cannot enter. So effectively, this mediates a photon-photon interaction between these. And yeah, nonlinear photon-photon interaction, and a lot of people have looked around this and achieved a lot of very, very beautiful results, including some from here by the group of Gerhard Rembe, has of course been doing beautiful experiments on this. Now, basically as a theorist, there's a lot of fun going into this, and I worked a lot with it, but it is single atom physics. So at least at the first take, the theory is rather simple. So in terms of theoretical challenges, it's perhaps not the most challenging things, although there are a lot of fun things to do. A little bit more challenging it gets if we look at something like Rydberg interaction, right? So the idea here is that we have this cloud of atom, and then we can now send 2 photons in. And what happens when we send in 1 photon is that now we can absorb it into this cloud of atom. Now we can use lasers to excite it to the Rydberg state. And essentially what happens is that now this highly excited atom has a strong interaction with all the surrounding atom, which means that when I send in another photon, it will see a different medium, and therefore effectively there's now an interaction between these 2 photons. And of course, a lot of people have also worked on that and made a lot of beautiful experiments, including here, where again, Gerhard Rembe's group has been doing beautiful experiments on this. Now, the physics is more rich because now it begins to be a many-body physics problem, because now there are many atoms, still few photons, and now a theorist has been playing around and having a lot of fun discussing, what happens in these systems. Now, it's a little bit funny, right? Because these here are the most studied systems, but there is sort of conceptually a much simpler system where we can realize this kind of physics. And that is sort of a 2-level system interacting with photons in this waveguide here, right? So what I'm going to look at is I'm just going to take this single atom here, put it next to a waveguide, and I'm going to assume that it is interacting strongly with photons moving in this waveguide here. Okay, so this here is conceptually much simpler. And this is, of course, where theorists usually would start. So what you do is you send in 1 photon, and if you only have 1 photon, this photon will just be emitted and it comes out again if the interaction is strong. Now, if you send in 2 photons, I should remember to say, now the only effect of this having this atom here is that this photon here comes out a little bit later. It is delayed. Now, if I send in 2 photons on the other hand, then what can happen is that now only one of these photons can excite the atom, right? You cannot excite it twice because it's a 2-level system. So essentially what happens is that the next photon comes in, and then there is this saturation effect, but there's also stimulated emission. So essentially this system here will have a tendency for the second photons to stimulate the emission of the first. And essentially what happens is that now these 2 photons come out together. And in particular, they also come out faster because the combination of only one of them getting delayed and stimulated emission means that the delay is smaller and they come out faster, right? So this here is, at least from a theoretical point of view, probably the simplest systems in which you can get these nonlinear interaction between photons. It is much less studied than the other system. And of course, there's a reason for that. And that is that until recently, it was the other things were the only things that worked experimentally. And it's no fun to do theory if there are no experiments around to prove that you're right. Okay, but now the situation is a little bit different. Now we actually do have a system. Oh yeah, I forgot to say, these photons come out together. So it's very important for the rest of what I will say is that essentially these photons tend to attract each other. Okay, because they come out together. So effectively I have attraction between the photons. Yes, but what I was about to say was that the situation is different. In recent years, people are beginning to make systems where they can have essentially perfect coupling between two-level systems and propagating photons. So one of them is this system here that my colleague in Copenhagen, Peter Lodal, is using a lot. So what he's doing is he's taking a piece of gallium arsenide, and then he is putting in some quantum dots, and he's drilling some holes. Essentially, what these holes do is that they act as a waveguide, so that light can only propagate in this waveguide here. And in this way, he can achieve a very, very strong coupling of his quantum dot to the waveguide. He says he can couple this one here with like 98% to this waveguide here. So if the photon emits, the quantum dot emits a photon, only with 2% probability does it go to the side, or with 98 probability it goes into the waveguide. So you can actually now have very, very strong coupling. Another system where we can see these kind of physics is if we go to the microwave regime. Now people can make superconducting qubit. And what you can do is now you can have, for instance, this system here where you have a waveguide. And now you can place your superconducting qubit. And then you can have interaction between your qubit and now propagating photon in this superconducting wire. And yeah, this one in particular is for cavity, but people have also made it sort of a freely propagating photon. This system here is essentially loss-free. Of course, there are other issues and other imperfections, but at least this issue here of decaying to the side is almost gone. All right. So what I want to ask in this talk is which kind of physics we can study with systems like that, looking at the interaction between the photons. All right. So again, is this really something we can see in experiment? Yes, indeed it is. Here's an experiment done by in the group of my colleague, Peter Lodal, where we said, okay, let's try to see if we can really see these interactions between the photons. So what we do is we take a two-level system, put it in the waveguide, and then we try to send in photon. So now what you can do first is you can send in one photon. You can solve the math. If this is strongly coupled, what you find is that with a high probability, this photon here will be reflected. Now, what happens if you send in two? Well, do the math again. There's now a high probability that they are transmitted, simply because the first one saturates the atom, the second one comes by and stimulates the emission, and they both go in the forward direction. Okay, so if there's one photon, it is more or less always reflected. All right, so now we look at what happens, right? So we send in photon, and now we condition on having two photons in the output, and we record their time. We send in them holes. Okay, so first up here, let's see if I can find this. Here we say, okay, now we send in two pulses, sort of different time, and then we look at where do the photons go, look at their time delay. So now there should be zero interaction between the photons. The photons should come out uncorrelated. And this is indeed what you see. If you look at some of these plots over here, you will see that there's now no correlations between how the photons come out. This one here looks more complicated, but it is just a probability distribution in that direction, the probability distribution in that direction multiplied together. So these are now uncorrelated photons coming out. We just use as a reference. And now we look at what happens instead if we send in the two photons together. And I think the cleanest example of seeing what happens, this is for a long pulse. What we see is that now two photons always come out together. Now, and they come out together and they always come out at the same time, right? Because if it's like one going and then one going, they don't interact. But if we send them together and we see where do they go, we indeed see that they come out at the same time, okay? Now we can make the pulse shorter, and well, some messy things happened. And well, we can understand this and we can model it theoretically. It is a combination of these two things, saturation and stimulated emission, and we can see that. But yeah, I don't want to get into the details of that. The main thing is that the top and the bottom is different, meaning that the photons indeed do interact. All right. Yes. So let's now go on to something sort of more theoretically interesting because this was just one, and I said we could solve everything. So let's now have many atoms, and then now let's. So what these many atoms do is essentially now they make a nonlinear medium. Okay, so now these photons can fly around in here, and they will have a non-interacting. They will interact, meaning that my photons will be flying around, colliding, doing something. There will be an interaction between them. So basically, what we hope to make here is a strongly interacting photon fluid. Right, so Emmanuel is very good at making atoms interact in, structures and DCs and I don't know what. Now we want to do the same with photons, where we have a many-body system consisting of many photons, and now there's strong interaction between those photons. All right. So, of course, why we want to do this is an open, strongly interacting, non-equilibrium, many-body quantum system. Okay, I really made an effort to see how many buzzwords can I squeeze into one sentence. This is how many I could think of. So this all applies, of course, but yeah, this was maybe not the most serious. But can we really begin to make such systems? Well, here's a first attempt at doing this in Copenhagen. Now we're just trying to see, can we couple emitters? So we took, this waveguide here, again from my colleague Peter Lodal, and now we find 3 quantum dots in there. And now we then try to, for instance, excite one of them. And what we can do is that we can then tune them in and out of resonance. If these have the same, if they have different energies, right, a photon emitted by this one doesn't care about the other one. If they have the same energy, a photon can be emitted and hit the other one. And so now what we try to do is we see if we can do this. So what we do is that we excite, just one of the emitters, pi pulse, excite it, and then we see what happens. And then we take, just count the photons. So first what we can do is if they're off resonant, we just have a standard exponential decay, just standard exponential decay, 1 quantum dot decays, nothing interesting. Now we tune them into resonance. What happens? Well, we see this one here, first a fast decay and then a slow decay. Okay, so this is what is known as super and subradiance. You can basically take this one here, excited state here, and you can decompose it into a plus superposition and a minus superposition of being excited here and here. If it's plus superposition, the dipoles are in phase and you have a rapid decay. If it's a minus superposition, the dipoles are out of phase and you have a slow decay. And this is indeed what we see here. With a certain amplitude, we see a fast decay. And then after a while, all the fast ones have decay, and what is left are just the slow one. Okay, so now we can indeed begin to see that this photon, these quantum dots here in this waveguide are actually interacting. They are exchanging photon emitted from one to another, and we begin to have sort of interaction between them. So we are not there, but we are moving in this direction. Okay, yes? Yes. 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 But there's one issue, and one issue is the subradiance. The subradiance because it couples badly to the waveguide. So for the subradiation, there's a large probability that it decays to the side. Yes. All right. Okay, so basically this is a system that I'll be playing with, except that I need to introduce one more ingredient that is sort of important for mainly technical reasons. And that is something called chiral coupling. Okay, what is that? Well, here is a waveguide that, Peter can make. And there's one I've tried to sketch that this is not just perspective, that this is not on top of that. I've tried to sketch that what they have do is that they have these holes and then they have shifted them by half a lattice spacing. Okay, so why is that important? Well, now you can imagine that basically light bounces back and forth between these holes, and you can just ray trace that, there's a ray going like this. Let's look a little bit more now at what happens to the polarization of light. Okay, so let's say this is half a wavelength. So now this polarization will be opposite to that polarization. And then, opposite that. Now, what you should look at, for instance, is a point like this when I a little bit start playing the movie, right? Because now this one will move first in this direction and then in this direction. And that will mean that the electric field at this position here will be pointing in different direction. Okay, so if I see the movie here, you see that it now moves in sort of different directions. Okay. And if you look at the polarization here, what you will see is that it goes like this, like that, like that, and like that. So if you are at this particular spot here, what you will have is circular polarization. Not linear, but circular polarization, just because there is this delay from going here, and then the electric field comes back and points in a different direction. So this is a classical picture. You can also do it, sit down and solve Maxwell equation. What you find here is that indeed you have circular polarization. Why is that important? Because suppose that I put an atom in there which has a transition that only talks to one of the polarizations. Now, what I didn't tell you is that this circular polarization here, the direction of circular, depends on whether I'm going to the right or to the left. Okay, so for the one going to the right, for instance, I have sigma plus polarization. For the one going to the left, I have sigma minus polarization. So what this means is that this atom here, which is here, it will only decay in one direction, right? So here is a simulation. They have also seen it in experiment where they said that let's say that we have a quantum dot sitting here, and then they now in this case simulate where does it decay, and you can see there's nothing going in this. It all decays to the right. Okay, so this is just a little bit trick, which is convenient for some effects that we can turn on and off with our decays with the same probability to the right or to the left. Okay, so the model I'm going to consider is that we have now atoms which can be placed a distance d apart, and they can be excited or they can be in the ground state. And yeah, we assume for simplicity for everything I have to say today that they only decay to the waveguide. They don't decay to the side. They can decay to the left or the right. Sometimes it's different, sometimes it's the same. It doesn't make a big difference for the physics. It's just nice to have this switch to turn off and on and off. All right. So of course, as I said, I'm a theorist. So how do we describe this mathematically? Well, there are two ways of doing it. It's about light and matter. And of course, light and matter are connected by Maxwell's equation. So if you have one, you have the other. So the solutions are either you solve for the light and then you can find the matter, or you solve for the matter and you can find the light. And depending on the problem we are looking at, we either do one or the other. For instance, if we would like to have something coming in, it is pretty convenient that we know what is the light state, and then we typically solve it in terms of the light. People can sort of analytically write down if we know what is the light coming in. There is just a simple formula relating to what is the light coming out, for instance, for a two-photon state. It's just an analytical formula. It is written down in this paper down here. You can go look it up. We use this when we are considering light propagation, and mainly in the chiral direction, because then we can just boom, 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 boom. This scatters to this, to scatter to this, to scatter to this, to scatter to that. And it's pretty easy to use this formula. Other part of the time, what we do is we integrate out the field, assuming that the light moves at an infinite velocity. And then what we are left with is just an effective Hamiltonian describing that the atoms interact, right? So I can have one emitter emitting and then being absorbed a different one. And there's a phase associated with it, which depend on the propagation phase that the photons pick up in between. So that will be an important parameter. Is this K naught D? What's the phase that it picks up, right? And so now we have an effective atomic Hamiltonian. It is non-Hermitian because if I have an atom chain, light can emit at the ends, but for most of the time, I'll be considering an infinite medium, and then it doesn't really matter. All right, so now we just have a coupled spin model that we can sit down and we can solve and we can play around with it. All right, so now let me talk about the physics that come out of this. So let me do the easy part first and start with one photon. Okay, so what's the one photon physics here? Well, we have some atomic states. Up here, they have a well-defined frequency independent of, K. Doesn't matter, how I make, my atomic energy is the same on all. I can go to K space, and then it's the same for all K, right? Then I have my light field here. Light has a dispersion relation, which is just linear. I'm really not good at using this pointer here. Okay, light has a linear dispersion relation. And at some point, of course, it crosses the atomic state. Now I can sit down, I can solve the equation using Bloch's theorem, and I can find sort of the polariton energy. And basically, it looks like what you would expect, right? So you have interaction. So you have an avoided crossing here. So you have one band going sort of the upper one and one which is the lower one. Now, of course, light moves at the speed of light, which is fast. So this one here, which is tilted at 45 degrees or whatever in this drawing here, of course, turns into basically vertical, because light moves so fast, right? So once we solve it, we end up with this picture down here that, we have various branches, okay? Now, and a little annoying thing is, this is how the picture looks nice when I think about it in physics. Now there is this issue that when you do solid state physics, you can always choose the Brillouin zone at will, right? So now mine, in this case, runs from minus pi to pi. That is in my head the easy one, which is the one which is easy to understand. In the paper, we actually made it from 0 to 2 pi in many of the papers we wrote. So that just messes it up. This is the same picture. You should just, imagine that this half here is move over here. So many of the pictures are going to look like that a little bit. Sorry about that. Okay. But yes, you can recognize here some features. For instance, you can see that if you are far away from atomic resonance, then basically your solutions are free photons traveling at the wave number of photons. Or you can go sort of away from those places here, for instance. Then you have states with essentially atom-like frequency, meaning now you have atom-like state where the photons move slowly. So these polariton, depending on where you are in this picture, they can either be atom-like or they can be photon-like. And of course, if they're photon-like, they move fast. You can also go in and you can actually define these as, you can find an effective mass. So around these points here, you have a quadratic dispersion relation. So now basically what happens is that your photons or your polaritons get an effective mass, and we can sit down and we can calculate it. It's just given by this very simple formula down here. Okay, so in this regime, basically our photons require mass. And also something will play an important role is that there's a band gap with a width set by essentially the decay rate of the atom, gamma. All right. So that was sort of what happens in an infinite chain. We just have these polariton propagating, which can be atom-like or it can be photon-like. Now we can also see what if we have a finite chain. We can go out to the edge and we can see what happens. And of course, if a polariton travel towards this edge here, what it can do is that it can sort of be transmitted or it can be reflected. And now it's pretty easy to see that what you do is basically you do the same as in your quantum mechanics 1 course when you first studied scattering. Right, so you say there's something propagating to the right, something propagating to the left, and now with a reflection coefficient, you can write down the Schrödinger equation and you can solve it. And what you can find is now what is the transmission probability. Okay, and we find something like this, that at some point it is 0, meaning everything is reflected. And at other places, everything is transmitted. So when is everything transmitted? Well, if you go back and you look at the dispersion relation, then you can see that the place where everything is transmitted, this is the same as this K naught D, meaning if your excitations is photon-like, meaning it basically flies past the atom without interacting with the atom, what will actually happen at the edges will continue. But if it is now heavily, dressed by the atom, it's basically an atomic state. Then when it gets to the edge, it is basically reflected. And we can go from this one regime to the other, that if it's photon-like, it just exits. And, the more atom-like, the more reflected it is. All right. So that was just, atom-like it's reflected, photon-like it's transmitted. So this was just one, us solving the equations of motion for this single polariton. So let's try to see what comes out of that. So here's one example of where we try to use these result for something. So one example is superradiance, super and subradiance, right? So as I said before, if the dipoles are in phase, you can have strong bursts of light coming out. If the dipoles are out of phase, you can also have, suppressed emission, that nothing comes out. How can we understand this in this language? Well, now I can just look at states near k equals 0 in the dispersion relation. So now I basically have this standing wave here. It's just a particle in a box. I solve that, and I have a standing wave with a k, which is pi over nd. I have this long range. All right. And now what can happen, of course, is near the edge, I can have losses. And those losses have a fairly simple, you can get them fairly simple, right? What's the decay rate from the edge? It's the density times the group velocity times the transmission probability, right? It just says that everything which comes to the edge, they travel at a certain velocity, they come out there, and with a certain probability, they go out. So now we can begin to add in stuff. For instance, the density goes as 1 over n. If I have one photon in there, the group velocity, we can sit down, we can calculate, is proportional to k because we have massive photons. And the transmission probability you can see down here is actually also proportional to k. Multiply all of these together and you have that the lifetime of the subradiant state goes as gamma divided by n cubed. So if I now have 10 atoms placed correctly, I have a superradiant state which is basically lives for 1,000 times longer. Okay, this actually completely agrees with what people have found in the literature before. Yu Chang and Klaus Møllmer, they looked at this, and indeed they find the scaling here. And yeah, if you do it more carefully, even the factors of 2 fits. Okay, so basically in this picture here, what subradiance is a polariton moving around, and then every time it gets to the edge, it has a probability of being transmitted. It's not saying something wrong, that something wrong, it's just a different picture of how we can describe it. All right, but that was just one. So let's see, we can move on. The natural generalization from 1 is 2. So now we see what can we do with 2 photons. And of course, the natural thing to consider first is scattering. So now we can have 2 photons, and now we can let them scatter, and we can see, do these photons scatter? And so to describe this theoretically, what we do is we say, okay, let's look at a system which has a certain center of mass momentum, because momentum is conserved in the system, so that's a good quantity. And now for each center of mass, we can make a wave function ansatz. And we just have some center of mass momentum, and then we have a wave function of the relative coordinates. We can now sit down, make an ansatz, and we can begin to look at solutions. And if you look at near k equals 0, what we can say is we have an e to the I qx, basically something moving like that, and then it scatters, and then there is some transmission, amplitude, and then you have e to the minus I kx moving back, right? So it comes in and scatter. You can sit down and you can solve, and basically what you find is a picture like this. So this is the transmission amplitude of the scattering here between 2. If the photons come in, if they come in very, very slowly, then basically what you find is you have a complete phase change in the scattering, right? They come in, and then in 1D, everything which comes in has to come out. And so the most extreme effect of scattering you can get is a phase of -1, because this one is because they're boson. This one is equivalent to this one. So the only effect of scattering, most extreme effect of sort of scattering in this case you can have is you get a -1. And indeed, if they come in at low frequency, they get, the scattering phase of -1. And indeed, if you look carefully at it, by the way you can describe this is to say that these photons coming in have like a delta function potential. If you just make the continuum theory saying that, they are delta function, you get this dash curve here. And you can see that it fits pretty well in this thing here. So what you can think about is these photons here, they just move around in 1D. They're massive particles, and they have a scattering amplitude corresponding to there being a potential between them. And we can solve exactly what it is. Of course, this continuum description breaks down when the wave number begins to be comparable to 1 over the distance between them, because then it is not a continuum theory. Okay, now exactly how this goes depends a little bit on what's the density of the atom here. This is with a low density, which is where it's high density, the atoms are close together per wavelength. This is where you sort of most closely resemble sort of continuum. The continuum comparison breaks a little bit down if there's a sizable difference between them. All right, but we can more or less understand this. Okay, and we can do it all analytically. Now, of course, when I asked my student to calculate this, they came back and said, no, we cannot do it. And I said, no, come on, this is simple scattering in 1D. You should be able to do it. And they couldn't get the equation to fit and came back to me again. And after 3 or 4 times, we realized that probably there's something we have forgotten. And indeed, if you just try to solve this scattering problem in that way, you'll realize that it doesn't work. You cannot make the equations fit because we've forgotten a physical effect. And that comes from the fact that now there are multiple bands, right? If it's just massive particle, they would just scatter and that would be all they could be. But now, as I said, there are different bands. There's this upper band and there's this lower band. So what can actually now happen is that now you can change band. So you can have 2 photons here in this band here. They can collide and then they can create one here and one here. That fulfills what do you call energy and momentum conservation. Okay, so you can have these inelastic where they come in, change band, and then go out with a different velocity. Okay, we can sit down and we can solve this analytically. We get a complete mess. So this here is the probability of having a elastic collision. So in some region it's 1, in other region it sort of drops. Yeah, we can understand this. I'm not sure I can make any much sense after the physics of this, but we can understand it coming from these, band and how so on. And if I play around with the parameters, I can actually define spots where I have complete inelastic collision. All right, so this is like the most extreme case of 4-wave mixing. When 4-wave mixing, normally take 2 lasers, and then they do something, and then 2 new frequency cannot come out. Now, if you play your parameters right, you can do deterministic 4-wave mixing of 2 individual photons. So they come in, and with probability unity, they switch to a different frequency and come out both shifted in frequency. So this here would be the extreme case of 4-wave mixing. All right. Okay, but this was scattering. I can also move on and talk about bound states, right? Because these photons here, they attract, so can we make them bind together? And so in recent years, sort of the interest in bound states came out of this paper down here, where they just solved the scattering dynamics for a single atom, and then they asked, how does it look? And then they found various solutions, and one of the solutions they found for 2 photons was this so-called bound state solution, where this was like an eigenstate of the scattering, and they interpreted this as being a bound state of 2 photons. Now, I looked at this and I said, what bullshit. I didn't believe it. No way, this is not true. This is not a bound state, because what is a bound state here? You have 2 photons scattering off. Is that really a bound state? So I didn't believe it. And so my first thing I wanted to do was I wanted to understand, is this really a bound state? So the reason why I didn't like this is, to me, a bound state is a property of a medium, right? I have, something can be bound in a medium and not bound in a different medium, right? If you take salt, it is not bound in in water, but if I put it in oil, it is actually bound. So the medium can make it bound and so on. So this was more I was thinking. This here was more like a point thing, so I didn't think it. So what I wanted to figure out first was, does it actually make sense to talk about these bound state as physical entities? And so what I asked my postdoc at that time to do was to now look at the medium and then try to solve the equation in this medium here and see, can he actually find the bound state? So what you do is you write up an ansatz like this, and you have two, and then you have a center of mass of the bound state, and then you have relative coordinates. Then you look for solutions of the relative wave function. Indeed, you can do it. There are two types of solution. One is free particles, where they basically just propagate, or you can find one which is the same bound state as before, only now it is in space. So instead of where it was before in time, I need to divide by the group velocity. But essentially, I find exactly the same bound state. We were very happy, and I told the postdoc, we should publish this. This is really cool. We understand it. And then he told me to check the Russian literature. Indeed, this bound state for this system was found all the way back in the 80s. So I was depressed. They even found the n-photon bound state. So then the question is, okay, it seems that they are bound. So what does it mean that they are bound, right? So can we see some kind of physical consequences of them being bound? And so what we wanted to do is, again, we wanted to send them in, and we wanted to understand these bound state properties. And so the effect we were looking at is, again, this delay, right? So what happened, as I talked about you before, if I send in one photon, I will just excite my emitter, and it will emit again. And there will be a delay. And you can calculate this delay. It is called the Wigner delay. For a chiral system, it is 4 divided by gamma. I don't know why it's 4. You solve the equation, you get 4. Okay. So now what happens if we send in 2? Well, right. So now there is this process of stimulated emission. So if I take in an M photon bound state, right, only one out of the M photon gets delay. And also the delay goes down by a factor of 1 over M, because the other M minus 1 photons stimulate the emission. So from these arguments here, you expect that the average delay goes as 1 over M squared, where M is the number of photons in the bound state. Now we can solve the dispersion relation. And indeed, this is exactly what we found. From the dispersion relation of the bound state, what we exactly find is that there is this delay 4 divided by gamma divided by M squared. So indeed, this very simple picture here agrees perfectly with what we get from the dispersion relation. All right. So bottom line is, if the photons are bound, they move faster. So how would one see this in experiments? So here is a simulation where we just assume we send in a coherent pulse. So this contains 1, 2, 3, 4, as many photons as you like. And then we try to calculate what comes out. So first, there is, if you have one photon, whoops, let's see if this works a little bit better. If you have one photon, you would expect 4 divided by gamma, which times the number of atoms, and you get something around 80. Now, if you have a 2-photon bound state, you would expect it to come out, 80 divided by 2 squared, which is 20. And indeed, we see a peak. Is it really a 2-photon bound state? Yes, because we can also calculate G2. What's the probability to have 2 photons? If we look at the 1-photon peak, well, there are no 2 photons. If we look at this peak here, exactly, we have 2 photons coming out. And we can, of course, continue with 3. If we now have 80 divided by 9, that's somewhere here. Here we expect to see a peak in intensity coming from 3 photon. And indeed we do. And indeed we see that G3 peaks there. And of course, now we can continue if we want to. Here's for 60. Now we can resolve 2-photon bound state, 3-photon bound state, 4-photon bound state, 5-photon bound state, 6-photon bound state. And indeed, for instance, the G6 peaks around the time where we expect the 6-photon bound state. Okay. So this here would basically allow you to see that, okay, now my bound state comes out differently. They move differently. So I really see this effect of the bound state. All right. Then let's try to do something different, right? Because I claim that they're bound. How can I prove that they're bound? Well, let me try to split them apart. How can I split them apart? So here's another little calculation we did. So now we assume we have two waveguides. Both of them have these two-level atoms in there. And now we assume that in between the atoms, they can tunnel back and forth. Okay. So what would we expect? If they are not bound, there would be nothing preventing them from jumping back and forth at random. Whereas if they are bound, we would expect them to jump like this, or like that, or like this, or like that. Okay. So let's do the calculation and see what comes out. Okay, if we did, if there were one single photons, they would be coming out at this time here. And now two photon bound state, we expect to come out here. And indeed, now we have set up the parameters so that we see most of the light coming out in this bound state. And now it's a little bit hard to see. Unfortunately, that's the physics. There's a blue curve and there's a red curve and there's a black curve. Blue curve is two photons being here, black curve is being like that, and red curve is being like that. So what you see here is that in this simulation here, basically the two photons don't change. They stay where they are. Okay, I can make that more quantitative. I can now look at photons coming out during this time. This is photons where I don't expect them to be bound. And then I see what is their dynamics. Well, they can both be in the upper, they can both be in the lower, and they can be one in each. And basically what you see is Rabi oscillations, sort of independent particles. I've set up my conditions such that each photon have done like a Rabi flop between being in one and the other. And in between, they are one in each. Okay, so this is exactly as you would expect for particles where, they are not at all bound. They don't care about each other. They just propagate at will, jump back and forth randomly. What happens if you look at the other one? Well, for these parameters here, what I find is that basically they stay in the same waveguide. They do not jump, right? Because they cannot do like this because they are bound together. But in this case here, I've set the tunneling so small that it's just too little probability that they can do like that. Therefore, they just stay in one, and they just stay there, and they propagate as a bound state. Okay, what if I change the, So again, the conclusion is the bound state really is bound. They stay together when we try to pull them apart. What if I increase the tunneling? Then indeed, now I begin to see this one jump back and forth. But something else happens. Now, if you look carefully, there's both a red and a blue curve here. Signifying that now they are actually in two, but I also see that there are two peaks. And the student showed me this and said, I think there's an error in my program, and we looked for a long time to find the error. And in the end, we started believing it. So what we figured out that what is happening here is that now there can be two different types of bound state. The bound state can be here and here, okay? But it can also be here minus here, or it can be here plus here. And what happens now is that, the bound state where they have a minus is this peak, and the bound state where they have a plus is this peak here. In the plus, there's a small component where they can sort of do like this, but they do this with very small amplitude. So mainly it is here plus here. Okay, so I have different kinds of bound states coming out. All right. Yes, and I can play around them, and they play around with different. Okay, I can also do something else. I claim that these bound states are different specific physical entities. Let's try to bang them together and see something happening. So let me say that I put up a situation like this. I have a single photon in front and my bound state afterwards. My bound states will now move faster. And this will mean that at some point these will collide. And I can now begin to play CERN physics. I begin to do collision experiment. And let's see what happens when I, bang stuff together and see how they collide. So here's a little simulation of that. So here we have, single photon, and the bright one is two photon. The two photon is brighter because they're two. And now you can see that, this is essentially, this is how we did it. This is a measure of time, how much they delay, and this is their position. If they move fast, it would be a vertical line here. Okay, so the two photon again moves faster. So what we see is that, you know, this one here moves ballistically, the single photon, except that here it gets delayed a little bit more. Whereas if I look at the other one, it moves here ballistically, and then it gets a little bit accelerated. So what is happening is these are coming in together. They are now attracting each other, interacting a little bit, and then move apart. So apparently I can make collision experiment between my bound states. And this collision here that we simulated, the bound state survives. I don't know if you can also sort of smash them apart by doing more violent collision. All right. Yes, it's stable. So, but now, of course, you may ask, what are they actually? And well, you know, one way to get some intuition about it, suppose that I go to big detuning and large number of photons, then you would expect to be able to make a mean field description. And indeed, you can. So if you are far detuned, basically what happens is that your atom, now your photon, now interact with your atomic transition. You can adiabatically eliminate the excited state, and what you end up with is an effective basic index of refraction, which goes as gamma over n times the density of atom. Now, what you can do is that, of course, if you have a strong light field, you excite some of the atom, meaning that your density goes down. And your density goes down exactly proportional to the number of photons you have. Now you plug this into your Hamiltonian, and you have an effective A dagger, two photon interaction with a coefficient going as 1 over d tuning cube. Okay, so now you can take this Hamiltonian and you can now begin to do mean field description. And one famous result coming out of that mean field description is you get solutions which are solitons, right? So electric field, these are the ones we use to send telephone signal across the Atlantic and stuff like that. So you can find a solution where the electric field of such a soliton goes as gamma t divided by the number of photons. What is happening is that your photons are attracting together. So you have this stable wave packet which try to spread because of dispersion, but then the photon attraction attracts them together, and the more photon you have a smaller and smaller wave packet. Now I can similarly calculate the electric field of my m photon bound state in the limit where m goes to infinity. And what I find is exactly the same, only sort of this mean number of photon is replaced by the number of photons in the bound state. Okay, so basically what this is telling you is that, well, you take solitons, which are a well-known classical solution, you let the number of photons in the soliton go to not 0, but to 2, and that's your 2-photon bound state. Okay, but this was sort of off resonance. What if they are on resonance? Well, the way to understand that is you can now sit down and calculate the Rabi frequency. And now you can take these two Rabi frequency and you can integrate the Rabi frequency from 0 to infinity. And then in this bound state, what you get is 2 pi. Okay, so what this is saying is basically this bound state here is a solution where I do a 2 pi rotation on my emitters, right? So I come in, I do up, and I go down. These two photons, their Rabi frequency, do a 2 pi rotation. This is again known in sort of the literature. This is known as self-induced transparency because I don't have any loss because I exactly do a 2 pi rotation on all my emitters. So it's never in the excited state. And I have a very, very stable solution that lives for a long time. Yes. So again, the conclusion is this is a soliton solution and my bound states are just the quantum limits of these classical solutions. Okay, how am I doing on time? I'm supposed to finish soon, right? Up to 5 minutes. So I need to skip something. Okay, so let me just say, you know, do something very, very quick. Bottom line is that now we can also solve all of this. Let me go to this one here. And then I will want to spend the time and talk about something else. We can also solve these bound states in the non-chiral regime. Now it looks much more complicated. It is not So basically what happens is, if I remember I had these two bands. If I take two photons from the upper band, I get some states up here in the blue. If I take two photons in the lower band, I get something down here in the orange. Okay. So now if I take two photons in the blue band, right, remember these are massive particles, particles attracting in 1D always have a bound state. So I would expect that, some binding energy below the continuum of my bound state, I would have a bound state. About my, of my two photon state, I would have a bound state. Indeed, we see something looking like it. Similarly down here, now everything is inverted because the mass is negative, so binding energy is positive. So again, I see some, something here close to the continuum, only bound. But now there's also some green stuff here. And those green stuff here are where I've taken states where I've taken one from one band and one from another band. So a particle with positive mass and negative mass. Okay, so now what we begin to look at these bound states at different places, they begin to be, show different features. So one state is down here. That's a true bound state. That's basically because here there turns out to be a gap in the energy spectrum. So now there are no free particle states where the photons are not bound at this energy and momentum. So if I have a state there, there's nothing that it can decay to, so it's stable. So this is a true bound state. At other places, right, so this here would be a bound state of two particles in the lower band, but because they can make these inelastic collisions where I change to a different band, it actually, my bound state dies after a while. So this is scattering resonance. So it becomes bound for a while and then it decays. And then there is this particular bound state here, which is it is in the continuum, but it lives forever because the density of state vanishes. So it is kind of a bound state or a scattering resonance with infinite lifetime. All right. But now let me spend 3 minutes talking about many photons. Okay, so as I said, we would like to do many-body physics. So let's say that we now take photons, which are now near this place here, meaning near k equals 0. So now we have massive photon. We have a contact interaction between them. Massive particle with a contact interaction. This is known as the Lieb-Liniger model. It's the same as one-dimensional BEC. And now there's a slightly funny thing that you should realize. And I've said all the time you have attractive interaction, and indeed that's true. But when you solve scattering of a short-range potential in 1D with an attractive potential, what happens is actually all the attraction goes into making a bound state. And if you then look at the free particles, they are actually repelling each other. Okay, even though it's attracting. So now photons, we were looking at the free particles, so photons actually repel each other. Now, this is very, very famous because the ground state of for the unfold bound particles in the dilute regime is actually exactly solvable. It's known as the Tongs-Giardeux gas. Okay, so it's interesting because basically what happens is what we call fermionization. If you write down the wave function, then basically it is given by this Slater determinant here, which is how you describe non-interacting fermions. Of course, this now has a different symmetry. So what we need to do is we need to add a phase factor in front. This is just a phase factor. But apart from this phase factor here, what you essentially have is now you have this fermionic wave function of your bosons. All right. So the heuristic explanation is why this fermionic wave function is good. And this is because we have repelling photons now. And indeed, if we take the Slater determinant and put two particles on the same side, they don't, the wave function is 0, so they're never on top of each other. Another way to say it is that there's this scattering phase here, which basically comes when I look at the wave function of two particles which are close together. They get this -1, and this is the same as the -1 you get when you interchange fermions. All right? And if you don't believe me, ask Emanuel Bloch, because they did the experiment with atoms here, and here's a random plot from their paper. Indeed, they see this Tongs-Giardeux gas. So what we want to do is now we want to do this Tongs-Giardeux gas. Can we find that state as a stable state of my atom, of my photons? And indeed, as I said, the heuristic explanation is that you get a -1 on scattering. And as we sort of, I showed you this before where we calculate the scattering phase, indeed we get the same. So it seems we can make it, but there's one issue. In the case of atom, it is the ground state, and therefore it's stable. Now you can ask, is this state stable? And in particular, there are many places where the photons can get lost. They can, just make this inelastic collisions, and you can also have losses at the edges. So now we can sit down and with all of this formula for how the photons behave, we can actually figure out how big are these rates. And what we find is that, for instance, the edge scales as basically here, the density cube, and then times 1 over m because it only happened at the edges. And similarly, in the Tongs-Giardeux gas, we find that the inelastic collision scales as density to the 5th. So if I just make my gas of photons dilute enough, it should be possible to make this Tongs-Giardeux gas. All right, and it's stable. So conclusion, I started playing around with this system here, and it turns out that there's surprisingly rich physics. There's a lot of fun physics effects going on. They have this scattering, which can be elastic and inelastic, deterministic frequency shifts of photon collision, bound states of the photons, different kinds of bound states, scattering resonances, and so on. And even if you go to many-body, at least this Tongs-Giardeux gas should be possible. In terms of outlook, what I would like to do is we would like to see, can we see similar effects in 3D? In particular, it would be fun because the experiments are not perfect, but maybe if we can find similar effects in 3D, then Emanuel Bloch could do it in an optical lattice or something like this. So this would really be fun to see if we can find similar bound states. And in fact, people have in 3D system found that there's 3D solutions where they have solitons. So now we want to see, can we take that to the quantum limit where you only have 2 photons? So these are known as photon bullets. And of course, if you think about photon bullets, it's only a question of scaling. Then we can scale this into photon torpedoes. And that was the Star Trek reference that I promised you. All right, another question is, now I've showed you that we can make this Tongs-Giardeux gas and it's stable. A different question is, how do we actually get in there? Because now we cannot just cool it. Getting into that state and playing around with it is going to be hard. I have no idea, but at least it should be possible. All right, let me thank a lot of people. In particular, this was done, a lot of this work was done by Björn, who did all the scattering and the bound state in 2 waveguide. Yu Chang, Bastian, and Johannes worked on, understanding the non-chiral bound state. Johan worked together with Björn. This was all started when, Sahan was a postdoc in Copenhagen, where we just started playing around with this physical system. Then he moved to Hanover, where he started started working for Clemens. And Clemens thought, hey, wait a minute, this stuff you're doing in Copenhagen is fun, so let's join in. So Clemens joined in the project, then Derek and Giuseppe at ICFO, and all of this here has been a lot of collaboration with Peter Lodal and his collaborators on the experiments. All right, so thank you for your attention.